north-south trending mountain range, these eruptions occurred 6 to 7 million years ago. Each red asterisk denotes a probable vent. The Cove of Topaz Mountain, good place to begin.
Looks like we got a lot of territory to explore today.
And then we have these openings.
Maybe 100 crystals.
In this video, we're going to unpack topaz deposits in a particular formation environment of rhyolite domes. The Thomas Range of Utah is a prolific locality on BLM land for collecting gem quality topaz crystals. And inspired by a recent trip to the area, I present this informal case study of the Thomas Range with a focus on Topaz Mountain. We're going to begin with the geology, discuss how this mountain range was built, and then later get to the field and ultimately discuss how exactly the topaz is forming and where it might be most concentrated. The Thomas Range is a north-south trending mountain range in western Utah, primarily consisting of Miocene age extrusive igneous rocks. Extrusive means it's erupted above the surface of the earth, and in the context of the Thomas Range, the volcanoes began explosively, and towards the end of the period that they were active, they became more effusive, allowing lava to pile up into domes. Fission track and potassium argon dates reveal that these eruptions occurred 6 to 7 million years ago, which is after all of the orogenic events that built many of the mountains in the western US. Orogenic just means mountain building event. So what then was happening tectonically to form the Thomas Range? Well, not only can you form mountain ranges through compressional tectonics where you have convergent forces displacing material upwards, but you can also form mountains through extensional tectonics. And that was the case in Utah 6 to 7 million years ago, where the North American plate was being stretched, thinned, and then molten material was allowed to percolate up through, permeating the surface, giving rise to the volcanic chain that became the Thomas Range. The two dominant lithologies or rock types of Topaz Mountain and the Thomas Range are one, stratified tuff, which is the ash and ejected pyroclastic material from the eruption. And then number two is alkali rhyolite, which is all of these examples that we're looking at here and represents the lava component of the eruption. This is the geologic map of the Thomas Range. We'll go into more detail in just a minute, but for now I'll mention the different colors represent different rock types as visible from the surface. We're concerned with this area here, which is the rhyolite and the tuff, and I want to use this opportunity to show what the tuff is. The tuff is this heavy orange, and in this cross section, E to E prime, we can see down below, this is a cut through the landscape, and we can see that there's a volcano, that's Topaz Mountain, and the magma chamber would be below, feed the magma up this pipe where it erupts. In between these different pulses of rhyolite, we get this TTMT layer. That's the tuff, and this is the ash that was explosively erupted and distributed over an expansive area of the landscape. Ash can be found way far away from eruptions of volcanoes. So on the geologic map, the tuff is this orange layer, and in satellite, it is this layer right here. Zooming in, we can see that there's a color change, indicating a change in chemical composition, as well as a difference in mechanical properties. The tuff is a cliff-forming rock, and the rhyolite is the lighter color above it. I will note that all of the unique minerals that I collected was within the rhyolite. However, it's still good to know what the mountain is made of. In Google Earth, we can visually distinguish the rhyolite and tuff because it creates high relief topography, which means a steep and dramatic landscape. Rhyolite is felsic, so high in silica, and because of this, it forms a very viscous and sticky lava. This is evidenced by the steep flanks of the Thomas Range contrasting against the surrounding basins. The next question then is, where are the eruptive centers, or places where the magma and hot gases permeated the surface, and are they correlated with topaz formation? In order to answer this, let's focus our attention on the southernmost mountain within the range, Topaz Mountain. The geologic map of tertiary rocks in the Thomas Range actually shows us the locations of these eruptive centers, or vents, mapped by surveyors. Each red asterisk denotes a probable vent area, while the red lines show the trend of the rhyolite flows from the vents. The primary vent on Topaz Mountain occurs all the way at the top, which makes sense because this is where all the lava was erupting from. Also note that these visible, steeply dipping rhyolite flows are roughly concentric to the vents, or in circles like tree rings. The implications of this are that in the field, we can theoretically identify flow structures in the rhyolite and use them to locate these mapped vents and even map new vents. To see if there's a relationship between the vents and topaz deposits, let's plan a route across the landscape and document any occurrences. Since others have had much success in the South Bowl, otherwise known as the Cove of Topaz Mountain, I figured this would be a good place to begin. A first task would be to journey around the entire bowl, recording the distribution and quality of topaz along the way. Other rockhounds, such as the Crystal Collector, Nico Jackson, and that camping couple, have documented the cave as productive. The Rugged Rockhound also identifies a productive area known as the V, so these became waypoints while planning. I did all of my data collection and route planning in a phone application called Gaia GPS, which is great because it offers offline maps so you can stay oriented even when there is no signal. Also really great for rockhounds because not only does it offer geologic maps, it enables you to snap photos to your map so you can log any discoveries with notes. I am a Gaia affiliate, which means if you decide to purchase the app through the link in the description, you get 10% off the price and I get a small bonus at no additional cost to you. Day 1 begins here. The direction of the arrows indicate the direction of the route, and all of this will make sense when we get to the field section of the video. Day 2 begins here, looping around this way and back to the car. And then finally, day 3, up the mountain and back down the mountain. A final note is that BLM has designated the Cove of Topaz Mountain a public recreational rockhound site, which means you don't have to worry about claims because they revoked all the claims. The only exception is these guys right here. This is Topaz Dome location of Topaz Mountain Adventures, where you can pay for a variety of different packages to mine pink topaz, bixbyite, or even put a stick of dynamite in the ground and mine topaz the old-fashioned way. Without further ado, let's begin this 9-hour drive and get to Topaz Mountain.
I hop out of the car and the first rock I actually step on, there's a topaz. Just right there. Is that luck or are they just that abundant? Good morning, Utah. Let's see what we can do with a full day of sunshine. We're gonna check all the way up to the peaks of these mountains today. Walked up, noted any topaz development along the way. Small crystals. Now I'm just below this peak and we have the ridgeline here, and I've gotten to the first place that actually looks very interesting. It's really soft. It's just like dust that chinchillas roll in. I don't know, maybe something going on here. I just want to roll around in it. These as well, that I'm gonna classify it and we'll see what's in these. Oh yeah.
Classified, maybe 100 crystals. They're all small, but they're all really clean.
This way, up on those, and across this whole face, where is the most topaz coming from? Because later, we're gonna go over to the backside and check there as well.
This is the first vein that I've seen, and with little topaz crystals growing out.
In this dome, we can see some fabric of the flow of the rhyolite. And all of these little polka dots, these phenocrysts, are topaz crystals. They're pretty sandy. Yeah, really sandy composition. I think we should try another place down around that way. Continuing along that direction, there are larger topaz crystals here. Very sandy composition again, but we'll see if there's a mix of quality in this specific location. Classified 3 pans, one from here, there, and then around the corner, and all of them are sandy. Next spot over, a good place to classify. Seeing some clear crystals on the surface, distinguished separation between mechanical properties of the flow of rhyolite. 3 baskets I decided to come up a little in elevation to go over, and almost looks like a cyclic twin. It looks like we have a nice trail to follow. There are glimmers of topaz up here, but I'm not seeing anything like what we were encountering on that slope. You may be curious why the ridgeline discontinues right here. The reason why is because there is a fault that runs directly through this valley. On the geologic map, we're standing right here looking across the valley, and the fault runs right through it. Where it's bold, there's evidence of the fault, and where it's dotted, it means it's concealed by alluvium or surface material. Meander. And we're gonna wander and meander up that way. Coming from the pass throughout this entire region, it's barren. Not even any sparkles on the surface. Let's continue further that way and then come through this valley, and absolutely no topaz in this area. Only at this lower elevation am I beginning to notice some glimmer on the surface. Just came from that ridge and first occurrence of topaz. Only at lower elevation. Confirmed that there is a correlation with elevation here, because here I am noticing topaz crystals. Smaller, but you can even see them glimmer in the sunlight, whereas up above there was nothing. Coming this way, they've gotten larger and clean. Brian Major dug in this spot, the crystal collector. I've grabbed as much as I can out of that. It's all so soft and workable. So I'm gonna classify it and we'll see what's in the pan. Looks pretty good to me. In certain regions, it's just easy to work with. Oh, I just got a new mineral. They're iridescent and they're hexagonal. This spot seems pretty good, and I'll be able to work that one out. That one for sure. In between breaths of inhaling topaz dust, I just looked in it and there it was. Red beryl. Love. I'm gonna get a tarp and then put it down and drop this stuff. It's just dense in this area. There's another one. Well, the cave is looking pretty good. Just an FYI, we're at 95 counts per minute for ionizing radiation in the cave. So about 5 times the average. Quality is comparable to what we were finding over there. We need to pick up the pace. I'm not even stopping until I see something larger and really sparkle in the sunshine. On the same wash, but I want to show this because this is a really great example. This stuff actually looks blue. It's got a different crystal habit than the topaz. I mean, it really looks like quartz. Today, walked up this, went back and around to here, and then came across this way. major things I've noticed, I've collected maybe 60 carats of topaz so far, and all of them are occurring at lower elevation. Where I am now is vacant of topaz. Everything is like microscopic. So the route now is to go down this way, explore around all that area. Really, really white. Continued down from that ridge, and these were on the surface, and this is all fresh because that just came out of it. Some pockets are just on the ground level. A few ridges north, and the crystals, I mean, that would be a spot if there were one classified, and they're all just microscopic. We're going to continue north into this section of the bowl. That up there looks interesting. It's a lot lighter colored, and after checking that out, we're going to come over this ridge and then through this section and then make our way into this where it's all light colored, and continue that way all the way to the crystal cave. After that, the entire bowl will have been mapped, at least at this contour where crystals have been determined to enlarge in size. In pinpointing other locations where topaz is occurring, there's two things that I'm doing at every creek crossing. One, classifying, nothing here, and two, checking all the vugs in different colors of rock, because it have all come down these valleys. So this gives us an idea of what's up above. Also, there's two types of veins that I've noticed here. One, this what looks very much like calcite, but it's not, because it's incredibly hard. This formed in between two layers of rock, and I've seen them in place. And here's an example of one as is. One thing about it is it's incredibly hard. And two, I'm not 100% on what mineral it is. In some places it does show crystal structure, but here not so much. I will show one of those examples. Here's an example of the other type of vein where we have topaz crystals encased in calcite. Calcite and the chalcedony are both epithermal minerals. So epithermal means shallow depth, low temperature, hydrothermal solutions precipitated these minerals in any available cracks. And this happened after the formation of the topaz. We came from there, walked around, no topaz formation in any of these creeks or in the rock. This is the white patch, and we are at the ridgeline, so we might as well walk over the back and see what it's like on the other side as well. Wow, not really what I was expecting. Let's head down in elevation just a bit, because the rock down there is a lot lighter, and up here it's pretty consistent and homogeneous. No topaz thus far. This area looks like it has potential. Let's check the base of that cliff. Once we go down there, wow, rhyolite is so psychedelic. Your feet just grip it. Like, look at that. Just ripples in the rock. I am in love. So alien. And the very first crystal on this journey. After having walked around the entire canyon and seeing what the rock looks like in its natural state, you can tell where people have been breaking it up and searching for crystals. This is the first occurrence around the bowl at this contour of topaz. I didn't even know there was more than one cave, or this is the beginning of one, but the consistency is just the same, and it makes sense because we are directly below the other cave. Yeah, there's the other one. And notice the structure. This joint right here runs directly up. Yeah, you can see multiple lines. And they run right in sequence with that cave up there. Here comes the snow. But this is why I wanted to journey around the back of the bowl today. Sun is up. Day 3. Let's check out what's on the backside. Looks like we got a lot of territory to explore today. Up here it's looking pretty good actually. I just followed some float and it turns out that Utah float is just gemstones. And then I got curious and noticed that this is a vent. Do you see how altered it is and how granular? So I just started hammering away at it and there are topaz crystals. So let's get them out and check the quality. Quality is good back here. The vent structure comes up this way. I followed it up and that was just one face was exposed. All of this was just dust. That one behind it. These vents is where it's at, further up here. That's actually looking good back there. Some clear, some darker. I'm gonna move up. This is the consistency that you're looking for. Soft, like flour dust. I'm gonna classify it. Okay, let's see if we can find a bigger one. Northwest, sandy, but let's check it. When you have all this white with topaz on the top, it's a sign that you need to classify. Looking good. Popped over another ridge line and notice all of these just sticking out of the rock. These are topaz, but they're really sandy. However, just because you're getting sandy topaz doesn't mean that there's not clean ones nearby. This rock was sitting exactly here. I popped it up and check out what's underneath. I just put all this silt back to recreate it. And it's all just soft. Beneath this is what I popped up. Just like that. Doesn't look like anything underneath, but you don't know until you check. Let's take a moment and observe what's going on here. This is all hard rhyolite. And then we have these openings that are semi-open. And then this stuff is really bleached. This is the pocket material. So ultra white, the rhyolite is just gray, a lot more solid. And then you get that stuff. This is what's coming out. That's what blocked the pocket. It's soft. And then we get sandy. I'm gonna go get some tools and pop all this stuff out. Here comes a hungry gatherer. Hello. I made a mixed nut salad. Goodbye. I got gear and just popped this one up facing the back
can tell when you're getting into a pocket because all of the flour gets golden brown, like brown sugar.
I noticed it was a little bit golden in the base. The best crystal to come out of there was this one. And what led me to both of these spots are these, which I found just on the slope. So I came up and there are more. That rock had to go, so it went, and there's some crystals behind it. But more importantly, what you should make of any float that you find is that it's not just a random occurrence, that there is some feature that can be tracked. And here it is a linear one. On both sides, there are topaz crystals. So I'm following that now, and it looks like we've got another pocket here. We can infer from this situation that we should keep following that up around into that, pull that rock down completely, and then also continue back down that way. Really soft rock. It continues to produce. And this is that hexagonal platy metal crystal. There's just so much mineralization, and then a series of topaz crystals. All came from up in the top. Let's take this down. I just saw a little glow of amber, and then that one. Good morning, Utah. As you can see, we got a storm coming in. It should be about 2 hours before it starts raining or snowing or something. The weather's 50 degrees, so I'd expect for it to be rain and then go to snow. So we're gonna collect until it does, and then keep collecting after. I'm back to the vent. I did drop the rock down, and I'm just gonna pop out as many blocks as possible and just see how much topaz. Yesterday and all former days, the goal was to pioneer, explore, and collect. But today it's just collect in a high density zone. I also want to note that the topaz aren't coming from one single layer. It's multiple layers within this vent. The rock is really soft and workable, so the goal is just to break it up. Gonna pop this one out. Since we know what a vent looks like, I thought I'd find another where you have all this yellow, where the gas or fluid was passing through. It seems to me there's a correlation between the quality of the crystals and the softness, also the degree of alteration. This is really yellow, lots of different minerals, and the pockets are incredibly easy to pull away the stuff from the sides.
Here comes the sun. I don't know if it's gonna be good or if it's gonna be sandy. All I see is brown sugar. I was heading back on 70 and saw something shiny on the side of the road, so I stopped. It's selenite. Also, I don't know fossils very well, but I know the slang for these is devil's toenail. Some kind of sea creature. I found them on this, devil's toenails on that side. I'll put the coordinates in the description.
You may have noticed that many of the well-formed crystals were occurring in little bubbles in the rock. These are called lithophysae. Because rhyolite is the extrusive equivalent of granite, lithophysical cavities are just like myrolitic cavities or mineral-rich voids. The difference is that topaz forms at the Earth's surface in rhyolite versus at depth in granite. Both systems require highly evolved magmas enriched in volatiles like CO2, water vapor, and fluorine. As the molten rhyolite rises during volcanism, it depressurizes, and these volatile vapors exsolve from the melt. The same thing happens when you pop the top on a cream soda. Popping the top releases the pressure, results in bubbles of CO2 gas, which is a volatile. This is volatile exsolution, with the bubbles being the lithophysae in rhyolite. Volcanic eruptions release tons of volatile gases into the atmosphere, but during the final stages of volcanism, the lava cools and solidifies, which begins to contain the vapor in the rhyolite. The volcano continues to degas though, and this concentrates the chemical elements within the lava dome. When the saturated vapor cools enough, it triggers crystal growth along the cavity walls. And this happens by gas phase deposition, which is where solid crystals form directly from the volcanic fumes. Based on my research, I'm under the impression that the majority of rhyolite-topaz forms this way, as opposed to through hydrothermal solutions. I found that not all lithophysical cavities contain crystals, and that's because the distribution of chemical elements is not uniform across the lava field. And now we're getting into why some parts of Topaz Mountain showed very few crystals, while others were laden. Large crystals will form where there's a steady supply of volatile-rich vapor. These are the ingredients that are reacting with the walls of the lithophysae to build topaz crystal lattices. The source of these chemically concentrated gases is the vent, but based on the field data collected, I found that some of the largest crystals were found the furthest away from the center of the vent structure.
Okay, let's get oriented for a minute. This is the center of the vent. And in Gaia GPS, it's right here. So you would think that the largest and most abundant topaz crystals would be closer to the vent, because that's where all the gases were coming from. But this was not the case. I found the largest crystals here, here, and wrapping all around this section.
An explanation for this lies within the physical features that formed in the rhyolite as it cooled. As lava cools, it contracts, creating fractures and joints. And the locations of these structures is not random. There are patterns. To understand the patterns, let's consider the dome toward the end of volcanic activity. The entire dome is hot, and as it cools from the outside where it contacts the atmosphere, inward, accordingly, the fractures form at the surface and propagate inward, following the direction of the cooling front. This results in a fracture network that looks something like this, with the fractures becoming the secondary channels for gas. And these are what I was referring to in the field as vents. Though they're not the primary vent structure, they're secondary conduits that are connected to it. If this is the case, it could also explain the observation of more topaz being found at lower elevations.
I noticed that topaz decreased in size and abundance towards the tops of the valley walls throughout the entire mapping area. High elevations were closer to the surface, where volatile-rich gas was able to escape more readily into the atmosphere. Meanwhile, volatiles were better retained at depth, where the rhyolite was thicker, trapping it to promote crystal growth. A second structural control that likely governs where rhyolite-topaz deposits occur is permeability. As previously explained, volatile exsolution produces vesicles in the rock. Where there were higher concentrations of volatiles, more exsolution occurred, and the rhyolite became filled with gas voids. This may have initially produced some topaz crystals in those cavities, but because these cavity-rich areas are altogether more permeable than the surrounding rhyolite, additional gases could flow through these zones to produce larger crystals. This is essentially building on the existing lattices of crystals to grow larger, gem-quality collectible ones. In summary, the localized fracture networks and vesicle zones promote migration of gases through them and influence where the largest mineral deposits occur.
The power just went out, but we're going to continue. I hope that with the information provided thus far, you have a firm foundation of how topaz is forming in rhyolite-topaz deposits and are able to more easily identify the geologic features associated with its formation for a more enriched collecting experience. The power going out actually provides a beautiful bridge into the next part of the project, where we can discuss some of the fluorescent and phosphorescent minerals discovered in the cove. I'm going to name the minerals first, and then we'll talk about how they formed, which is by a different process than the topaz, which formed by vapor deposition. So we have amethyst and calcite with amethyst embedded, a hyalite opal, more hyalite opal, as well as chalcedony and calcite that fluoresces green, and then more hyalite opal in the back.
This set of minerals formed in epithermal vein deposits, which are shallow, low-temperature veins. Though volcanic activity waned at the surface, volatile solutions continued to circulate deeper in the magmatic system. Pressure changes at depth would send these late-stage hydrothermal solutions through some of the fractures to deposit silicate and carbonate minerals. We can tell that these minerals came later because they form a second generation of growth that encases the topaz crystals. Dissolving the carbonates reveals what the veins looked like before these secondary minerals arrived. Another unique luminescent property of topaz noted in this book by D.B. Hoover is that it emits light when heated. The thermoluminescent curve shows light intensity on the y-axis and temperature on the x. This peak tells us that when topaz reaches 250 degrees, it glows. The sherry topaz at Topaz Mountain are golden brown due to radiation-induced color centers. As I noted in the cave, the baseline radiation in the rhyolite of Topaz Mountain is 5 times what it is for granite. Radiation displaces electrons in the crystal lattice of topaz, producing a brown color center. Heating the crystals to 250 degrees imparts energy to the lattice, allowing electrons to move to lower energy positions. And this change in positions of the electrons releases energy in the form of light. Many minerals display thermoluminescence, though topaz does so quite intensely. Also notice that the crystal went from sherry brown to colorless. That's because the brown color center of topaz is metastable. The heat energy shifted the electrons back to their original state, resulting in a clear crystal. Ultraviolet light from the sun is another way that topaz becomes colorless. All of these clear crystals were found on the surface, while the sherry brown topaz were collected at depth, protected from the sun's rays. When a topaz is only partially buried, it results in a bicolor crystal. The sherry topaz from Topaz Mountain is photosensitive, meaning it will lose its color in the sunlight. Let's find out how long that color change takes. These crystals were collected from separate locations at Topaz Mountain. That one, the cave, you can tell by the surface texture. Going to be putting these outside in winter sun, so low angle of incidence for 3-hour intervals. Let's find out how fast they fade to colorless. At 15 hours of direct sun, there was a distinguishable color change. After 75 hours of the crystals being on the roof of my car, I accidentally drove away and needed to repeat the experiment. This time I chose one crystal with inclusions. The image quality changes halfway through because I got a new phone. At 12 hours of direct sun, a subtle fade was noticeable. At 156 hours, the crystal on the right faded completely, while the one with inclusions retained some of its color.
This crystal is still sitting in the sun and looks about the same at 249 hours, meaning the topaz with inclusions fade slower. Speaking of inclusions, what exactly are these inclusions? A variety of minerals can become encapsulated by topaz, though the majority of the black flakes here are specular hematite. The most common inclusion is actually quartz, which is a major constituent of the rhyolite host rock. Another principal component of rhyolite is an alkali feldspar called sanidine, and this too commonly gets trapped in the crystals. If lithophysae lacked certain volatiles needed to produce sufficiently large voids, the topaz that formed would be heavily included. This is because low egg solution limits the available space for topaz to grow into. If you're still with me, I love your dedication to learning about mineral formation. Let's do a giveaway for these fluorescent calcites, chalcedony, hyalite, opal, the amethysts, a topaz amethyst combo, amethyst on calcite with topaz, the bicolor topaz, hematite included topaz, 3 red beryl, and some topaz on matrix and clusters. If you wish to participate, write the words red beryl giveaway in all caps in a comment on this video. A winner will be drawn on the summer solstice of 2025, and there will be 2 more giveaways at the end of this video. Let's hop back into the fun technicality bath of topaz formation. The chemical name of topaz is aluminum fluorosilicate hydroxide. That comma between the fluorine and hydroxide means that the proportions of these anions can vary based on the geochemical conditions present during crystallization. Of all the genetic environments that gem topaz is known to form in, the temperature in the rhyolite setting is the highest. Citing D.B. Hoover in the Topaz book, the temperature of formation in the Thomas range is 630 to 790 degrees Celsius, or about 1300 degrees Fahrenheit. Hoover states that because of this, the hydroxide content observed in rhyolitic topaz is low. Changing the proportions of elements in the structure consequently affects the morphology of the crystals. Quote, when hydroxide substitutes for fluorine in the structure, there is a slight change in the unit cell dimensions. Pure fluor topaz is orthorhombic, but as hydroxide is substituted, at some point the crystal takes on lower symmetry, end quote. So in part, it's the variable chemical makeup that's giving rise to all these unique shapes that we see in topaz crystals.
Let's do 2 more giveaways. Actually, these for the autumn equinox, plus these, plus these.
To enter the second and third giveaways, comment your favorite color of topaz. This can be any color that topaz forms in, and write it in all caps and make it the first word of your comment, just so I know who's participating. 2 winners will be drawn on the autumn equinox of 2025. Hopefully this project inspires some to take a trip to the Cove of Topaz Mountain. Furthermore, this information can serve as a roadmap for prospecting areas surrounding vents further north in the Thomas Range. Don't be intimidated by geologic maps, they're not that bad. If it inspires you, here are some tips to take with you. Start with the float. Use my routes as a guide, but it may serve you to deviate. Target the lighter colored zones of rhyolite and walk until you catch glimmers of light on the surface. Also avoid topaz hunting during sunset and sunrise, because the best time to catch luster is when the sky is clear. Follow the float to locate a source, the secondary vent structures. These will take the form of fractures, that is, narrow irregular cracks, and joints, which are more linear. In doing so, look for ultra-white and yellow-colored rhyolite, which indicate alteration from vent gases. The rhyolite here will be softer. Heavily mineralized vent will contain hematite, so use that as an indicator mineral. Finally, there doesn't need to be an abundance of lithophysae for it to be a good zone, though those areas are good too.